Hi, welcome back. Today we're going to talk about recip engine theory of operation. Most general aviation recip engines operate on a four-stroke cycle. The four-stroke cycle refers to the strokes of the piston as it goes up and down within the cylinder. And each stroke in the four-stroke cycle has a name: intake, compression, power, and exhaust. Now the piston can only go two ways, towards the top of the center and the bottom of the center. So in order to get four strokes in, the piston has to go up and down twice. And in order for that to happen, the crankshaft has to turn completely around twice. And that gives us an intake, compression, power, and exhaust stroke. So we only get one four-stroke cycle for each two revolutions of the crankshaft. Another way to remember this is suck, squeeze, burn, and blow. So we bring in a charge of fuel-air mixture, we squeeze it down, we light it on fire and burn it, and then we blow it out as exhaust. So we'll start with the intake stroke. On the intake stroke, the intake valve opens up and allows the fuel-air mixture that's in the intake manifold, where fuel and air has been mixed together, to be drawn into the cylinder by the piston moving down in the cylinder. And by the way, just as a reminder here, we refer to the directions up and down to refer to the top of the cylinder and the bottom of the cylinder as pictured here. In the actual aircraft, we'd be talking about sideways, but it would get really confusing to refer to it as left and right because the cylinders are pointing in different directions. So when we say up and down, we mean just as pictured here. So as the piston moves down in the cylinder, it draws in a fresh charge of fuel-air mixture. And it gets drawn down by the rotating crankshaft. If you've only got one cylinder, you have to count on the momentum of the crankshaft to draw that piston down. If you've got multiple other cylinders, like for instance on a four-cylinder engine, there's probably a cylinder out there doing a power stroke someplace. You're taking a little bit of energy from that cylinder in order to turn the crankshaft and pull this piston down and draw this fuel-air mixture in. Then we're going to continue to do that during the compression stroke. Now the piston is moving up. The intake valve has closed, and in fact both valves are now closed. So there's nowhere for this fuel-air mixture to go, and we're just squeezing it down. And we're doing that in order to really concentrate that potential energy. And then we light it off with the spark plug and we burn that fuel-air mixture. And as that burns, it expands massively, pushing down really firmly on that piston. And this is where we get our power stroke. It would have been nice actually if they'd called it a torque stroke, because that's what it really is. We're putting a torque force on the crankshaft with that piston moving down in the cylinder. Again, both valves are closed here, otherwise it would just squirt out. Once we're done and the piston is down at the bottom, we open up the exhaust valve, and as the piston moves back towards the top of the cylinder, we push all of this exhaust overboard. And then we start the cycle again. And so it goes around and around. Each time it finishes, it starts over again at the intake stroke. So it goes intake, compression, power, and exhaust really, really fast. The intake and compression is one revolution of the crankshaft. The power and the exhaust is another revolution of the crankshaft. Here's an animation of it moving really slowly so that you can see what's going on here. And up at the top you can see the cams. We're picturing an overhead cam engine here, so we don't have to worry about push rods and rocker arms and things like that. We've got the cam mounted right on the top here, and it's pushing the valve open each time it comes around. Each of the valves has its own cam in this case. As the piston comes down, it's drawing in a charge of fuel-air mixture, which is colored yellow here. And you can see the fuel being mixed with the incoming air up here at the top with the carburetor. Once it gets down to the bottom, we squeeze that fuel-air mixture down, on the compression stroke with both of the valves closed, and then we light it, and that's when it turns red there momentarily. That pushes the piston down, and then as the piston comes back up again, the exhaust valve opens, and we shove the exhaust valve over. And so if we this is moving slow enough that we can actually talk through it if we're on the ball here. So we're looking at intake, compression, power, exhaust. Intake, compression, power, exhaust. As you can see, it takes 2 revolutions of the crankshaft to get through those 4 cycles. Pictured down below, just for general interest, is a little oil pan with some oil in the bottom of it, and that's where the oil drips back down. We'll talk more about oil systems later, but the oil always finds its way back down to the oil pan when we're done with it. So there's a couple of concepts that you need to understand when operating a 4-stroke aviation engine. And one is compression and the other is manifold pressure, and they're kind of related. So the compression ratio is the ratio between the bottom dead center and top dead center volume. So if you draw the piston all the way to bottom dead center and measure the volume of the whole combustion chamber, and then you run it to the top dead center, there's still some space left in there, and you measure it again, then the ratio between those two is the compression ratio. In other words, how many times bigger is the space when the piston is at the bottom than it is when it's at the top. The intake manifold pressure is what we, as a pilot, allow into the cylinder during the intake stroke. The more pressure we let in during the intake stroke, the more pressure there's going to be when we light that fuel on fire, and the more pressure we're going to get during the power stroke. Whatever pressure we allow into the cylinder during the intake stroke is multiplied by the compression ratio during the compression stroke. Now, you don't have to worry about what that number is. As a pilot, we're really only looking at the intake manifold pressure, not at the pressure after compression, but it's important for you to be aware that a small change in the intake manifold pressure makes a big difference on how much pressure you have at the end of the compression stroke. So that's why you'll find that when you start operating aircraft where you have a manifold pressure gauge, the changes in power settings are quite small on that gauge. That's because each of those changes is getting multiplied by that compression ratio inside the engine. Here's a picture that sort of shows that change in volume. We have the volume in the blue here at the bottom dead center, the volume at top dead center in yellow, and the difference between those, the ratio between those, is the compression ratio. So here we have a cross section of a piston and cylinder assembly, and it's on the intake stroke. And I've drawn in sort of a absolutely bare bones rudimentary intake manifold, which in this case consists of a pipe. And I've drawn a throttle valve in there, which is at this point wide open. So this would represent full throttle. At full throttle, we're letting in all of the pressure that the atmosphere has to offer us. As we close the throttle, we restrict the flow. The engine is over here demanding fuel air mixture, but we've put a restriction in, and so the fuel air mixture between the throttle and the intake valve is now under sort of what most people would call a vacuum, a lower pressure than atmospheric. We've drawn the pressure down. There's a number of abbreviations that people use for this, or two anyway, MP and MAP. MP is probably the most common. These two abbreviations could technically mean different things, and you may even find places in your text where they make a distinction, but for the purposes from a pilot point of view, they all mean the same thing. And we're talking about what you see on the manifold pressure gauge if the aircraft is equipped with a manifold pressure gauge. So at full throttle, manifold pressure equals atmospheric pressure less about 2 inches of mercury for friction. So we measure manifold pressure in inches of mercury just like we do atmospheric pressure. And even with the throttle wide open, the carburetor, the venturi in the carburetor, and the bends and twists and joints of the manifold, uh, the intake manifold, are going to result in a little bit of a pressure drop even at full throttle. So we're going to lose about 2 inches. So whatever atmospheric pressure is at full throttle, we're going to have about 2 inches less than that. As we reduce the throttle setting, we restrict the flow of fuel air mixture into the intake manifold, and manifold pressure is reduced. Typical cruise manifold pressure setting is between 20 and 24 inches, and there's exceptions out there, but that's a pretty normal manifold pressure setting. Typical manifold pressure for climb, also known as max continuous power, is 25 inches. The absolute maximum, what we call the 5-minute power setting, or sometimes takeoff go around power, is whatever we can get, maximum atmospheric pressure in a normally aspirated engine. In turbocharged engines, we could go even higher than that, but we'll talk about that later in the term. Atmospheric pressure decreases with altitude, so we're going to lose about 1 inch of mercury of manifold pressure per 1,000 feet, whether we're at full throttle or at climb or cruise. And so we may not be able to get our normal climb manifold pressure once we get past a certain altitude. For instance, if we went with this 25 inches of manifold pressure, then we're probably only going to get that up through about 3,000 or 4,000 feet, after which even full throttle won't give us 25 inches of manifold pressure anymore, and we'll just have to be satisfied with whatever manifold pressure we can get from there on. Here's a really good graph of what happens to the pressures inside of the combustion chamber during the four-stroke cycle. So we've drawn a charge of fuel air mixture in, and we go through the compression cycle, and the pressure is increasing as we squeeze it down with the piston. And then we light it off with the spark plug while it's still being compressed. We actually let it get a little bit of a head start in its burn there, so that by the time we get to the power stroke, we've got a burn well underway. And that's where its peaks pressure, the pressure peaks early in the power stroke, and then starts to taper off as the piston moves away from that burn front. But where the piston is being pushed down during that stroke, and then when it gets to the bottom, we enter the exhaust stroke, where the piston moves back up, but the pressure continues to drop because the exhaust valve is now open. And then we enter the intake stroke, where the intake valve is opened and where the piston is being drawn back down in order to draw in that new fuel air mixture charge. This is another really interesting representation of what's going on with the valves during the four-stroke cycle. It's interesting to note that the valves don't open and shut right at top dead center and bottom dead center of that four-stroke cycle. They lead things just a little bit and lag, and we call that valve overlap. So if we start here at the beginning on the intake stroke, you'll notice that the intake valve is open a little bit before bottom center. And so what this represents is everything on the right side of this diagram is with the piston moving down in the cylinder. Everything on the left side is with the piston moving up. And so the intake valve opens while the piston is still moving slightly up in the cylinder. And that's because the departing exhaust gases, which just happened, are have a velocity and a momentum of their own, and they in themselves will draw the new charge in behind them, even though the piston is still moving towards the top of the cylinder. And then the intake valve remains open all the way through that movement towards the bottom of the cylinder, and stays open a little bit past the bottom. And then that's where the compression stroke really happens, and and now both valves are closed at this point and remain closed through the compression stroke and almost all the way through the power stroke. We open up the exhaust valve a little bit before the piston gets to the bottom of the power stroke, so that that burning fuel air mixture can get those exhaust valves, the exhaust gases, moving through that exhaust valve quickly, so that we get that stuff exiting overboard as quickly as possible. And that exhaust valve stays open all the way through the exhaust stroke and a little bit into the intake stroke. Once again, we're using the velocity of the exhaust gases to pull in that new fuel air mixture. So a little bit complicated. Do you really need to know that as a pilot? No, I just think it's kind of interesting. It is built into the engine. It's not something that we have any control over. So all of that goes into creating the opportunity for the power stroke. Really, that's the only one of the four strokes where we actually get anything out of this particular cylinder. And what we actually get out of it is torque. And the torque is affected by several things. There's a couple of things that are designed into the engine. One is the diameter of the piston. The bigger the diameter of the piston, the more square inches the pressure has to push against, and therefore the more downward pressure you get. Also, the length of the journal on the crankshaft. The longer the length of that journal, the more leverage the connecting rod has on the crankshaft to turn it, and the more torque you get. So the trade-off there is that you get a really long stroke, then it makes it hard to get the engine up to a higher RPM. But those things are designed into the engine. What we have control over as pilots is how much pressure we let in on the intake stroke, and therefore how much pressure is generated during this power stroke. And that determines how hard we're pushing down on the top of that piston when we run the engine. So when you adjust the throttle, you are adjusting the pressure we're putting on the top of that piston. And that's the only really important pilot thing to take away from all that stuff. So again, that pressure is here during the power stroke. That's what we're adjusting with the throttle. Here's another picture of it, and they go into a lot of detail in our text. You can kind of skim over some of the stuff about the various types of pressures and so forth here, the mean effective pressure and so forth. It's an interesting thing if you're into engines. That's worth reading if you are. If you're not into engines, you can kind of skip over that. Just the big takeaway again is, as a pilot, you are controlling the actual pressure that is pushing down on that piston. Now that controls torque, but that's not quite power yet. So power always takes into account time. How fast are we applying a force? That's what power really is. 1 horsepower is defined as the force of 33,000 pounds over a distance of 1 foot in 1 minute. If you divide 33,000 by 60, you get 550. So a force of 550 pounds, 1 foot in 1 second, means exactly the same thing. It's still 1 horsepower. Just using seconds instead of minutes. So here's where it comes from. We're pulling coal up out of a mine with a horse. And what they found is a typical horse could pull 550 pounds of coal about 1 foot per second without breaking the horse. The faster the horse moves, the more energy it takes, the harder you're working the horse. And so if you want to pull that coal up twice as fast, then you're going to need 2 horses or 2 horsepower. It's a measure of the energy that it takes to accomplish the work of pulling the coal up out of the mine. So torque, work, and power. Torque in our case is the force, because we're turning the crankshaft around in a circle, and when you do that you talk in terms of torque. And we talk about that in terms of pound inches or pound feet. Work is a load or force through a distance, and power is the energy it takes to accomplish that work at a certain speed. The faster you work, the more energy it takes, or the more power. So when we're talking about turning something in a circle, the work that we do per revolution, the equivalent of the distance, is 2 pi times the torque. So how do we turn that into power? This is what's called a Prony Brake. And notice that it's P-R-O-N-Y, not Pony Brake, although pony would certainly make sense with horsepower, but that's not what it is. It's a Prony Brake, and this is where the brake comes from in brake horsepower. So what this represents is the end of a crankshaft sticking out the end of your aircraft engine. It's labeled propeller shaft here, but this is where you would mount the propeller. And that is presumed to be turned by the engine. So the engine's back there running right now, and this crankshaft is spinning. And we bolt on this brake, which hinges over here, and has a friction screw on the other side, so that as we screw down on this handle, it tightens the brake around the crankshaft, and it tries to turn the whole brake. The crankshaft tries to turn the whole brake with it, and we measure how hard it's trying to pull on that brake by putting a scale under the end of this arm. The more we screw down the wheel, the more it's going to push down on the scale. Now, so the way we would run this up is if we wanted to know how much brake horsepower this engine was going to produce at, say, 2,000 RPM, we would start the engine up, get all the brake and everything set, start the engine up, run it up to 2,000 RPM and start screwing down the wheel. And as the engine started to slow down, we'd add more throttle to get it back up to 2,000 RPM, screw the engine a little more, add a little more throttle, etc., until we get to full throttle, and the brake is holding it right at 2,000 RPM, and then we read the scale, and now we know the torque that we have at 2,000 RPM. Now, there's a formula that we can use to change that torque into power, brake horsepower. And the formula is 2 pi times torque times RPM divided by 33,000. So this takes into account how fast we're doing by including the RPM of the engine. So 2 pi times the torque basically gives us the work. The RPM gives us the amount, or this rate at which we are doing the work. We divide by 33,000 because we're using revolutions per minute, which is what our tachometers read. If we use revolutions per second, we would divide by 550 instead, but we don't. We use minutes, so we're going to divide by 33,000. So we're going to apply that formula now to the 152 engine. The manual on the model of 152 that I happen to have a manual for says 108 brake horsepower at 2,550 RPM. Therefore, let's do a little bit of the algebra that you swore you would never use in real life. 108 brake horsepower equals 2 pi times the torque times 2,550 RPM divided by 33,000. If we solve for torque, then 1 over torque equals 2 pi times 2,500 divided by 108 brake horsepower times 33,000. So we've moved the torque over to the left side of the equal sign and the horsepower down to the right side on the bottom. And then we rearrange that, we flip it over. So torque equals 108 brake horsepower times 33,000 divided by 2 pi times 2,550. We do the math on that, and lo and behold, we get about 222 pounds pound-feet of torque is what that engine is putting out. It's what it has to put out in order to create the horsepower at that speed. Do you need to know all that as a pilot? No. It's just interesting, and you will need to be aware that power and torque and RPM are closely related, and this is going to be something that you have to take into your career with you, because it's more important when you move from fixed pitch to constant speed for you airplane guys. It's also important for everybody when you move from piston into turbine aircraft, because this becomes just a crucial concept for running a turboshaft engine. So when it's a turboshaft engine, instead of brake horsepower, we call it shaft horsepower, but it's the same darn thing. And the formula is exactly the same. But when you get to your training manuals for shaft horsepower, you will oftentimes find it simplified. And what they do is they take the 2 pi and the 33,000 and they say, well, those are always the same. We don't need to even have those in the formula, because we can just do that math once, and that comes out to 0.00019. We're just going to call that K. We'll use T for torque, and the standard nomenclature for RPM is the letter N. And so shaft horsepower then can be simplified down to a constant times torque times RPM, period. You could use that same horsepower for your 152. Notice the things that you have control over as a pilot are torque and RPM. So and how we control the torque in a normally aspirated, or for that matter a turbocharged reciprocating engine, is the throttle. The throttle controls the torque. Now thrust horsepower is what we can actually use to move the airplane or the helicopter around. And thrust horsepower, we take the engine horsepower, the brake horsepower, and we multiply that by the efficiency of the propeller. And the most we can expect out of a normal general aviation propeller is about 80% efficiency for a VY climb, which means that in that 152, we're really only, out of that 108 brake horsepower, really only getting about 85 or 87 usable thrust horsepower to actually climb with. Okay, I'm going to break this up into another chunk here. Make sure that you follow this on by watching the chapter on lubrication and then cooling.